Hi everyone. In this video, let us discuss about VGGNet. So the full name of VGG is Visual Geometry Group, right? Visual Geometry Group, right? So actually it belongs to the Department of Science and Engineering of Oxford University, and it has released a series of convolutional network models beginning with VGG, which can be applied to face recognition and image classification from VGG 16 to VGG 19, right? So what is the purpose of this VGG research? It is to understand how the depth of convolutional networks affects the accuracy of large-scale image classification and recognition. In order to deepen the number of network layers and to avoid too many parameters, a small 3x3 convolution kernel is used in all layers, right? So the input VGG is set to an RGB image of 224 into 224 size, right? So the average RGB value is calculated for all the images on the training set image, and then the image is input as an input to VGG convolution network. So a 3x3 or 1x1 filter is used, and the convolution step is fixed. So there are 3 VGG fully connected layers, which can vary from VGG 11 to VGG 19 according to the total number of convolutional layers plus fully connected layers. So actually the minimum one was VGG 11, and it has 8 convolutional layers and 3 fully connected layers. So the maximum VGG 19 has 16 convolution layers plus 3 fully connected layers. So the VGG network is not followed by a pooling layer behind each convolution layer, or a total of 5 pooling layers distributed under different convolution layers. So here in this figure, you can see VGG structure diagram, right? So you can see that convolution plus ReLU, and this stands for the maximum pooling, and then fully fully connected plus ReLU, and then the next one is about the softmax, right? So this is basically image, and then you can see this is how the structure actually differs, right? So this is how the structure actually differs. So VGG 16 contains 16 layers, and VGG 19 contains 19 layers. So a series of VGGs are exactly the same in the last 3 fully connected layers, right? It is exactly the same as in the last 3 fully connected layers. The overall structure includes how many convolution layers that you can see: 1 set, 2 set, 3, 4, 5, right? So you can see that a series of VGGs are exactly the same in the last 3 fully connected layers. The overall structure includes 5 sets of convolution layers followed by a maximum pool. Right, it is followed by a maximum pool. The difference is that more and more cascaded convolution layers are included in the 5 sets of convolution layer. So each convolution layer in AlexNet contains only one convolution, and the size of the convolution kernel is 7x7, right? Right. So in VGGNet, each convolution layer contains 2 to 4 convolution operations. The size of the convolution kernel is 3x3. The convolution step size is 1. The pooling size, right? So step size is 1. The pooling kernel is 2x2, and the step size is 2. So the most obvious improvement of VGGNet is to reduce the size of the convolution kernel and increase the number of convolution layers, right? So using multiple convolution layers with a small convolution kernels instead of a large convolution layer with the convolution kernels can reduce parameters on one hand, and the author believes that it is equivalent to more non-linear mapping which increases the fit expression ability. So 2 consecutive 3x3 convolutions are equivalent to 5x5 receptive field, and there are equivalent to 7x7. So why do we use 3x3 convolution instead of 7x7, right? So here you can see twofold. One, including 3 ReLU layers instead of one, makes the decision function more discriminative, and two, reducing parameters. For example, the input and output are all C channels, 3 convolution layers using 3x3, right? And one convolution layer using 7x7 requires, so like 7x7 you can see, right? So this is how it is being there, right? So this can be seen as applying a kind of regularization to the 7x7 convolution, so that it is decomposed into 3 convolutions. So the convolution layer is mainly to increase the non-linearity of the decision function without affecting the receptive field of the convolution layer. Although the convolution operation is linear, ReLU adds non-linearity. We all know the function of rectified linear unit, right? So definitely what it does, it will add non-linearity. Now look at this table, right? So the first one is about image, 2x convolution, 224 into 224 into 64. So here this is the image, 224 into 224 into 3, right? So basically 3 stands for the kernels, I mean channels, right? Red, green and blue, right? So we all know this already. The first one is about image, 224 into 224 into 3, and there is no striding, no kernel. And after that, what is happening? Convolution, right? So convolution is 224 into 224 into 64. Here also you can see that it is convolution plus ReLU, right? So 224 into 224 into 64. So that is basically the convolution. Here you can see kernel size as 3x3 and stride is equal to 1. The activation function used is ReLU, right? And then the maximum pooling, again 64. So 112 into 112 into, right? So can you see that over here, right? So in the next convolution, we are getting it as 112 into 112 into 128, right? Then the maximum pooling is done. We get 56 into 56 into 128. And the next convolution, the output is 56 into 56 into 256. Then maximum pooling 28 into 28 into 256. And then the next convolution, 28 into 28 into 512, right? And then maximum pooling 14 into 14 into 512. And then the next convolution 14 into 14 into 512. Maximum pooling is 7 into 7 into 512, right? So if you multiply, you'll be getting this one, right? So then the fully connected is connected to 4096 neurons, and then 4096 neurons, and the output is limited to 1000 classes, and the activation function used in the output is softmax. We all know that the softmax is used in the output layer when we have multiple outputs, right? Since here we have 1000 output classes, we are using softmax as the activation function. In all the other places, ReLU is being used, right? So hope this is clear to you. So this picture is used when we introduce VGG16, and this is giving a lot of information about it. So right? So here how the training happens, like the optimization method is a stochastic gradient descent with the momentum, and here the batch size is taken as 256, right? The batch size is taken as 256. And then a regularization, L2 regularization is used. And here the weight decay is 5e power minus 4, and dropout is after the first two fully connected layers. So P is equal to 0.5. So although it is deeper and it has more parameters upon the AlexNet network, we speculate that VGGNet can coverage in less cycles for two reasons. One, the greater depth, and the smaller convolutions bring implicit regularization. Second one, some layers of pre-training, right? So the next one is about parameter initialization. So for a shallow network, parameters are randomly initialized. The weight is sampled from say 0, 0.01 and the bias is initialized to 0. Then for deeper networks, the first four convolution layers and the three fully connected layers are initialized with the parameters of the A network. So however, it was later discovered that it is also possible to directly initialize it without using pre-trained parameters. So in case to obtain 224 into 224 input image, each rescaled image is randomly cropped in each stochastic gradient descent iteration. So in order to enhance the data set, the cropped image is also randomly flipped horizontally and RGB color shifted, right? So let us look at the summary of it. A smaller 3 cross 3 convolution kernel and a deeper network is used. The stack of two convolution kernels is relative to the field of 5 cross 5 convolution kernel, and the stack of 3 cross 3 convolution kernel is equal to the field of view of a 7 cross 7 convolution kernel. So in this way, there can be fewer parameters. Three stacked three, I mean, instead of three stacked, what we have is like the lesser, right? On the other hand, they have more. The non-linear transformation increases the ability of CNN to learn features. So in the convolutional structure of VGGNet, a 1 cross 1 convolution kernel is introduced. So without affecting the input and output dimensions, non-linear transformation is introduced to increase the expressive power of the network and reduce the amount of calculation. So during training, first train a simple VGGNet A-level network and then use the weights of the A network to initialize the complex models that follow to speed up the convergence of training. So there may be a question like, why do we use 3 cross 3 convolutions instead of 7 cross 7 convolutions? 3 cross 3 convolutions using 3 non-linear activation function, increasing non-linear expression capabilities, making the segmentation plane more separable, reduce the number of parameters. For the convolution kernel of C channels, 7 cross 7 contain parameters and the number of 3 cross 3 parameters is greatly reduced, right? So what is the role of 1 cross 1 convolution kernel? It increases the non-linearity of the model without affecting the receptive field. 1 cross 1 winding machine is equivalent to linear transformation and the non-linear activation function plays a non-linear role, right? So the effect of network depth on results, in the same year, GoogleNet also independently released the network with a depth of 22 layers, right? So VGG and GoogleNet models are deep. Small convolution VGG only uses 3 cross 3, while GoogleNet uses 1 cross 1, 3 cross 3, 5 cross 5 model is more complicated, right? And on top of it, I can also say that here the smaller filters are used, but deeper neural network, right? And then it has 3 cross 3 convolutions, stride 1, pad 1, 2 cross 2 maximum pool, stride 2. So why do we use smaller filter? Stack of 3 cross 3 convolution layers has same effect of receptive field as 1 7 cross 7, but deeper, more non-linearities and fewer parameters. So when we talk about VGG 16, it has 16 layers, but its a error rate is 7.3 percentage, improved from 11.2 percentage model. The model did not win, right? So when we talk about this, here the parameters do not include biases, right? So it flattens cooling output, right? So finally, the more parameters are in the second part of fully connected. Clear? So this is what gives us a very good information about, we were discussing about A, B, C, D, and E, right? So here A, when we consider A, there could be 11 weight layers, and here again 11 weight layers, B 13 weight layers. So 16 weight layers, 16 weight layers, and 19 weight layers, right? So here convolution is also getting changed, right? So this is the basic comparison of it. Like whenever we learn, if we learn by comparison, it would be really helpful for us, right? So you can also compare AlexNet, VGG16 and VGGNet, right? Already we have compared AlexNet with the ZFNet, right? So here also we can compare with the VGG16 and VGG19, right? So as I told you here, there will be 16 layers and here there will be 19 layers. So let's just look at this, like here there is additional 3x3 convolution layer, here also additional one, right? Can you see the difference actually? What is the difference between VGG16 and VGG19? So there is some additional layers from this VGG16 to VGG19, right? So hope this is clear to you, right? So this is a video that makes you to clearly understand what is VGG16 and VGG19, and now we have also compared with the AlexNet and several networks, right? So this is, I hope that this is clear to you.
GoogleNet. So we have come across several architecture, and also we have seen some, we have attained some basic knowledge on GoogleNet. So we are going to have a deeper understanding of GoogleNet in this lecture. So what is GoogleNet? And GoogleNet was proposed by research at Google in 2014 in the research paper titled Going Deeper with Convolutions. This architecture was the winner at 2014 Image Classification Challenge. When compared to AlexNet, ZFNet, and VGG, the error rate in this GoogleNet was really less. We know that AlexNet was the winner of 2012 and ZFNet was the winner of 2013 and VGGNet was the winner of 2014. So why it won the challenge? Because the error rate was really less. And this architecture used techniques like 1x1 convolutions in the middle of the architecture and global average pooling. So we will study in detail about this 1x1 convolution and why it is being used and how that basically works. So Google proposed this deep convolution neural network named Inception that achieved top results for classification and detection in 2014. And the ImageNet large-scale visual recognition challenge, which is nothing but ILSVRC, right? ImageNet large-scale visual recognition challenge evaluates algorithms for object detection and image classification at larger scale. One high-level motivation is to allow researchers to compare progress in detection across a wider variety of objects that took advantage of the quite expensive labeling effort. And another motivation is to measure the progress of computer vision for large-scale image indexing for retrieval and annotation. So the problems Inception V1 is trying to solve was like the important parts in the image can have large variation in size. For instance, image of object can be in various positions and some pictures could be zoomed in and some other pictures could be zoomed out pictures. So because of those variations in images, choosing the right kernel size for performing the convolution operation becomes very difficult. Do you understand what I say now? Like the image of the object could be in various positions, or like when we check with the zooming also, it could be zoomed in or zoomed out. And at the same time, we have to choose the kernel size for the convolution operation, and choosing the right choices being a very big challenge. So we required a large kernel to extract information of object that is distributed more in the picture, and a smaller kernel is preferred to extract information of image that is distributed less in the picture. Am I clear? So one of the major approach to increase the performance of neural network in it is by increasing its size, which means increasing its depth and also its size. So bigger size of neural networks corresponds to larger number of parameters that makes the network prone to overfitting, and especially when labeled training examples are limited. So another drawback of this increased network size is increased use of computational resources. So if we use more convolution layers, if more convolution layers are chained, then they may result in more consumption of computation resources. So if these added capacity is used ineffectively, then computation resources get wasted. Then computation resources get wasted, right? So what could be the solution for this, right? So how this problem can be rectified, right? To solve these issues, it comes up with a solution to form a wider network rather than deeper, which is called as inception module, right? So we call this as naive inception module, right? So this performs convolutions on input from previous layer with the 3 different size of kernels or filters, especially 1 cross 1, 3 cross 3, 5 cross 5. So in addition to this, you can see 3 cross 3 maximum pooling. Outputs are then concatenated and sent to the next module, right? So what do we understand over here? The naive inception module performs convolutions of an input from the previous layer with the 3 different size kernels of 1 cross 1, 3 cross 3, and 5 cross 5, and maximum pooling is performed. Then the outputs are concatenated and sent to the next inception module. So what is the problem in this naive approach is, even having 5 cross 5 convolutions can lead to require large resource in terms of computations. So this problem emerges more once pooling is added. So to make our networks inexpensive computationally, the authors applied dimensionality reductions by adding 1 cross 1 convolutions before 3 cross 3 and 5 cross 5. So when we use 5 cross 5, it can lead to, we may require large resource in terms of computation. That's the reason 1 cross 1 convolution is being added before this 3 cross 3 and 5 cross 5. So now let us try to understand how these affect the number of parameters in the neural network. So now look at this. You can see this 5 cross 5 convolution with the 32 filters, right? So this is a 5 cross 5 convolution naive way. We have an input 28 cross 28 cross 192 and an output 28 cross 28 cross 32. So if the computation is done for this, this convolution operation is what do we have over here? This 192, then 32, right? And then we have 52 and 2 power 82, right? So when you calculate all this, it will lead to 120. Oh, see, look at the number. These many operations are required. These many operations are required, right? So To bring down such a great number of operations, the dimensionality reduction is being used. Clear? Right. So to bring down the greater number of operations, the dimensionality reductions can be used. So here it is done by convolving with 1x1 convolution with 16 filters before performing convolution with the bigger filters. So after dimensionality reduction, the number of operations for 5x5 convolution becomes, so what will happen now is, for this 1x1 we get 2408448, right? So this is for this 1x1 convolution, and for this 5x5. So do you understand? So these many operations we get. So now you add both, right? So you will be getting it as, right? So what is happening here? We get certain number of operations, and there is large amount of reduction in computation. Why do we say so? Because in the previous case, what we have seen was these many operations we had, right? Now the operation is being reduced. So after applying dimensionality reduction, there is a large reduction in computation. So let's see how the inception module becomes. Right now, look into this one, previous layer, 1x1 convolutions, 3x3 convolution, 5x5 convolution. So what you can see over here is, before 3x3 and 5x5 convolutions, 1x1 convolution is being applied, right? And here also you can see that after pooling, 1x1 convolution is being used. Even here 1x1 convolution. After that, everything is being concatenated, right? So GoogleNet was built using inception module with the dimensionality reduction. So totally it has 22 layers deep network and 27 with the pooling layers. So some people call it as 27 layers. They include pooling layers also. So they call it as 27 layers network, right? So all the convolutions, including the convolution inside inception module, uses rectified linear activation, right? So all the convolutions use rectified linear activation. The size of the receptive field in our network is 224 into 224, taking RGB color channels with mean subtraction. So you can see that 3x3 reduce, and then 5x5 reduce stands for the number of 1x1 filters in the reduction layer, right? So you can see 3x3 and 5x5 in the reduce. So, right, you can see that, right? 3x3 reduce, 5x5 reduce, which stands for the number of 1x1 filters in the reduction layer used before 3x3 and 5x5 convolution. So we can also see the number of 1x1 filters in the projection layer after the built-in max pooling in the pool project column, right? So all these reduction layers use rectified linear function as well, right? So GoogleNet is a 22-layer deep counting only layers with the parameters, and with that deep network, there may be some problems like vanishing gradient. So to eliminate these, authors introduced auxiliary classifiers that are connected to intermediate layers, and that helps the gradient signals to propagate back. So these auxiliary classifiers are added on top of the output of Inception 4A and 4D modules. So the last loss from the auxiliary classifiers are added during training, and it was discarded during inference. So the exact structure of the extra network on the side, including the auxiliary classifier, will be like there will be an average pooling layer with a 5x5 filter size and stride 3, and it results in 4x4 512 output for 4A, and right, and then we have 4 into 4 528 for the 4D states, right? So 1x1 convolution with the 128 filters for dimension reduction and rectified linear activation. A fully connected layer with 1024 units and rectified linear activations, and a dropout layer with a 70% ratio of dropped outputs, a linear layer with a soft max loss as the classifier, predicting 1000 classes as we have seen already. And like if you look at the systematic view of GoogleNet architecture, this is how it is shown basically. Like it consists of total 9 inceptions module, namely 3A, 3B, 4A, 4B, 4C, 4D, 4E, 5A, and 5B, right? So like now let us try to look into this last part of this. Like as we discussed, GoogleNet was the winner at 2014 that took first place in both classification and detection task, and it has top 5 error rate of 6.67% in classification task, and an ensemble of 6 GoogleNets give 43.9%. You can see over here 43.9% MAP on ImageNet data set, right?